Assalamualaikum and good morning. Today I will present the problem description for our artificial intelligence project, which is the 8PUZZLE problem. The 8PUZZLE is a classical search problem in artificial intelligence that is commonly used to evaluate the performance and efficiency of search algorithm. The puzzle consists of 3 multiple tree boards containing 8 number tiles and 1 blank space. The objective of the puzzle is to transform the initial configuration into the goal configuration by arranging the number tiles in ascending order while placing the blank space at the bottom right corner. To solve the puzzle, the blank space can move in 4 directions, which are up, down, left and right. However, the movement is only valid if the blank space remains inside the boundaries of the 3 multiple tree grid and swap position with one neighboring tile. This problem has a large complex search space. The total number of possible arrangements is 362,880, but only 181,440 states are reachable from a given starting state due to invasion party constraint. The number of possible moves also depends on the position of the blank tile. A corner position has 2 possible moves, and each position has 3 possible moves, and the center position has 4 possible moves. For the PIECE framework, the performance measure is to minimize the number of moves, execution time, memory usage, and not expanded. The environment is fully observable, deterministic, static, and discrete. The actuator are the movement of the blank space, while the sensor are represented by the current box state. Finally, the initial state used in this project is 1, 2, 4, 3 blank space 5 and 6, 7, C8, while the goal state is 1, 2, 3, 4, 5, 6 and 7, 8 and blank space. Each movement has a uniform path cost of 1, and that's all for the problem description section. Thank you.
Okay, so after we know the problem of the puzzles, we will move on for the implementation part. So I will explain how we transfer the core search algorithm into the use functional Python code and how we track their performance. So here for the first is we will see for the environment, rules, and the helper function. We got used to helper function, which is the get neighbors and the Matan distance function. So for overall, the get neighbor function is we set the rules of the game how we solve the 8 puzzles. So in this, you will tell the AI how this board how to move this board in a legal move and not try to slide the tile off the board or through a wall. We also declare our puzzle into the 3 countries board. Then we go mention that they are only up, down, left and right moved. Then we also set the legal move for the AI so they not try to like move the tile through a wall. So next we will for the second function is the Matan distance function. This function is used for the A style and the research to calculate how many steps of each type will be used from the type just at the current location to its goal current location. Next, we will see for the algorithm implementation. So for the first BFS search, the BFS we use the decrete, which is the first in first out. Then we will also declare the visitors, which is we will store all the visitor state. Then we will count the complexity tracker by we will count by the node expanded, how many nodes will be expanded using this algorithm search to reach the goal. Then we will also count for the max memory that we'll use for this algorithm search to reach its goal. Then we also list out how all the legal moves that already done using this algorithm to reach the goal. And next we will move for the depth search. So depth search we use the last in first out, so we call it the function stack. Then we also same like just now, we will store all the visitor state, the node expanded and the max memory that used. So for the last in and first out, we will grab the newest port configuration from the top of the stack. So which means it will move right on the top of the stack to check if the node is already in the correct location or not. Next, for the greedy search. For the greedy search is we got use the priority quit, which is you got call back the function just now, which is the matter distance, to count how the type just now is how close it to reach the goal. So it will a little different compared to the BFS and the DFS level. Then same, we also save all the visited node, all the node expander and the memory that used. In the greedy search, it also will choose which is the smallest distance way to reach its goal. Although it may not the optimal path, it will also choose the current best choice. Then we move for the A-star algorithm. A-star algorithm also same like the greedy, which is also use the priority quit, but it looks smarter because it got imply the mathematical function, which is the Fn equal to Gn plus the Hn. So it will also count the step taken so far plus the step remaining to reach the goal. So this will lead the A-star to find the optimal path to reach the goal. So with the formula just now, which is the Fn equal to Gn plus the Hn, it will prevent the A-star from getting lost in the deep and inefficient path. So for the next part, which is the algorithm complexity analysis runner. So in here, we got list up the initial state, which is the 124, 305, and the 768. And we want to reach the goal state, which is the 1, 2, 3, 4, 5, 6, 7, 8, and 0. So in here, we also will count the real world stopwatch, which is with the start time and the end time. So we will count how many time were taken for each algorithm to complete to solve the A puzzle to reach the goal. We also calculate the path taken, how long is if the algorithm if our initial state is unsolvable, it will print out unsolvable. So let's run our code to see. So this is our output, and we can see here the BFS, it reached the optimus, which is the 22 step, and the A-star also reached the optimus path 22 step. However, the greedy and the BFS, they didn't reach the optimal path. Then for the comparison of their result will be explained behind.
So now is the heuristic part. So for the puzzle problem, we design a pattern distance heuristic because uninformed search expand blindly, but our heuristic filter out wrong path early to save memory. The metric sum the absolute vertical and the horizontal grid steps. Each tail must take to get home. This match ensure grid rules and yields a much better cost estimate than just counting misplaced tiles. We apply these two algorithms. So which is the greedy search and the A-star. Greedy search use only the heuristic Fn equal to Hn. It is very fast, but research the best route because it ignores history. A-star search combine past steps with the heuristic Hn equal with Gn plus Hn to guarantee the absolute shortest path because Manhattan distance never overestimates real cost. It is invisible because a single tails move shift the value by exactly 1. It is consistent. These properties prevent A-star from wasting time on all steps, forcing a narrow, laser-focused search tree directly to the goal. So this is the Manhattan distance function, or it can be said it's the GPS for A-star and greedy search. So the first is declare the distance with the initial value is 0. and we do the loop interactive from 1 to 8 tiles, and we exclude the 0 because it is the blank space, and we declare the current ITX and goal ITS. So based on ITS, we find out the row and the column using the divide with 3 and modulus with 3, and we implement the Manhattan distance calculation to find out the Manhattan distance and return the distance. So
now let's just discuss on the performance of algorithm that we obtained from executing the code that we had developed. So first of all, let's take a look on the breadth-first search algorithm, BFS. So the time taken for BFS to find the solution is around 0.71 seconds. So this is the longest time taken for among all of the algorithm, and this is basically due to the DFS has explored the most number of nodes, which is around 90,000 nodes, and this also causes the DFS to consume the most memory among the algorithm, where it stores around 100,000 nodes in its memory. So the path length found for BFS is around 22, which is the optimal path for the problem. And next, let's take a look on the depth-first search algorithm, DFS. The time taken for DFS to find the solution is around 0.02 seconds. So this is basically due to the number of nodes that it explores is only 900, and therefore the memory consumed by DFS is also quite less to moderate, which is around 2,000 nodes. So the path length found for DFS is around 900, which is obviously not the optimal path for the problem. And now let's take a look on the greedy best first search algorithm. The time taken for the greedy algorithm to find the solution is only 0.001 second. So this is the fastest algorithm to actually find the solution for the problem, and this is basically due to the number of nodes that it explores is only around 100, and this also causes the memory consumption for this algorithm to be quite low, which it only stores around 200 nodes in its memory. So the path length found for the greedy algorithm is 42, which is not an optimal path for the problem. And lastly, let's take a look on the A-star search algorithm. The time taken for the A-star algorithm to find the solution is around 0.1 second, which is considered moderate, and this is due to the number of nodes that it explores is moderate, which is around 2,000 nodes, and this also causes it to consume a moderate memory among all of the algorithm, which it stores around 4,000 nodes in its memory. So the path length found for A-star search algorithm is 22, which is the optimal path for the problem.
For conclusion, this project successfully implemented and compared 4 AI search algorithms, which are BFS, DFS, greedy best first search, and A-star search for solving the 8PUZZLE problem. From the comparison, BFS was able to find the optimal 22-step solution, but required the highest memory and execution time. DFS was faster and more memory efficient, but it produced a very long non-optimal path. Greedy best first search achieved the fastest execution time using the Manhattan distance heuristic, but it still produced a suboptimal solution. Meanwhile, A-star search achieved the best balance between the optimality and efficiency by finding the same optimal solution as BFS, while using significantly fewer computational resources. For the final conclusion, this project proved that heuristic-based search methods are much more efficient for solving complex AI problems. The Manhattan distance heuristic successfully guided informed search algorithms toward the goal state much more effectively. In addition, optimization techniques such as memoization and DQ improve the overall stability and performance of the algorithms. Overall, A-star search was identified as the best algorithm for solving the 8-puzzle problem because it provides the best combination of speed, memory efficiency, and optimal pathfinding. So that's all from us. Thank you.